In September 1939, the same month Hitler invaded Poland, I published a paper that described something impossible. A star that collapses forever. Matter compressed to infinite density. A region of space from which nothing, not light, not information, not anything, can escape. Today you call these objects black holes. In 1939, we had no name for them. Most physicists refused to believe they could exist. The paper was titled, "On Continued Gravitational Contraction." My co-author was Hartland Snyder, a graduate student. We used Einstein's general theory of relativity to calculate what happens when a massive star exhausts its nuclear fuel. The answer was disturbing. The star does not stop collapsing. It falls through its own gravitational radius and continues falling forever. The endpoint is a singularity, a point of infinite density where the known laws of physics break down. I published this result and then abandoned the subject entirely. Within 2 years, I was directing Los Alamos. Black holes, as they would eventually be called, disappeared from physics for nearly 3 decades. Why? The answer involves physics, history, and the peculiar way scientific ideas can be ignored when they challenge fundamental assumptions. The problem of stellar death. Stars exist in a state of balance. Gravity pulls matter inward. Nuclear fusion in the core generates energy that pushes outward. For billions of years, these forces remain in equilibrium. But nuclear fuel is finite. When a star exhausts its hydrogen, it begins fusing heavier elements. Helium into carbon, carbon into oxygen, eventually iron. Iron fusion consumes energy rather than releasing it. The nuclear fire dies. Now gravity has no opposition. What happens next? For small stars like the Sun, the answer was known by the 1920s. After fusion ends, gravity compresses the core into a white dwarf, an object about the size of Earth, but with the mass of the Sun. The density is extraordinary. A cubic centimeter weighs approximately 1 ton. White dwarfs are stable because of electron degeneracy pressure. This is a quantum mechanical effect. Electrons resist being squeezed into the same quantum state. The Pauli exclusion principle creates an outward pressure that halts gravitational collapse. White dwarfs were well understood. They had been observed. They fit into existing physics. The trouble began when Subramanian Chandrasekhar asked a simple question. Is there a limit? The Chandrasekhar limit. Chandrasekhar was 19 years old when he performed this calculation, traveling by ship from India to England to begin graduate studies at Cambridge. He combined quantum mechanics with special relativity. Electrons in a white dwarf move at high velocities. As compression increases, velocities approach the speed of light. Relativistic effects become important. The calculation showed something unexpected. Electron degeneracy pressure has a maximum. Above a certain mass, approximately 1.4 times the mass of the Sun, no amount of electron pressure can resist gravity. A white dwarf more massive than this limit cannot exist. It will continue collapsing. Chandrasekhar presented this result to the Royal Astronomical Society in 1935. Arthur Eddington, the most famous astrophysicist of the era, publicly ridiculed him. Eddington's objection was not mathematical. He could not find an error in the calculation. His objection was philosophical. The result implied that massive stars collapse without limit. Eddington called this absurd and a reductio ad absurdum. I think there should be a law of nature to prevent a star from behaving in this absurd way, Eddington said. The physics community largely sided with Eddington, not because he was right, but because he was famous. Chandrasekhar's career was damaged. He eventually left stellar physics entirely and moved to other fields. But the calculation remained, the limit remained, and the question remained. What happens to stars above 1.4 solar masses when they die? Neutron stars. In 1932, James Chadwick discovered the neutron. Almost immediately, theorists realized that collapsed stellar matter might be supported by neutron degeneracy pressure rather than electron degeneracy pressure. The idea: at sufficient compression, electrons and protons combine to form neutrons. A star composed entirely of neutrons, a neutron star, could be far denser than a white dwarf, perhaps 10 to the 14th grams per cubic centimeter. A teaspoon would weigh 1 billion tons. Neutron degeneracy pressure might halt collapse where electron pressure failed. I worked on this problem with several collaborators in the late 1930s. George Volkoff and Richard Tolman helped develop the mathematical framework. We solved Einstein's field equations for a static, spherically symmetric configuration of neutron matter. The calculations showed that neutron stars could exist. They would be approximately 10 kilometers in radius, city-sized objects containing the mass of the sun. But there was a problem. Just as electron degeneracy has a limit, so does neutron degeneracy. We found that neutron stars have a maximum mass. The exact value was uncertain. Our equation of state for neutron matter was crude, but it appeared to be somewhere between 2 and 3 solar masses. Above this limit, even neutron degeneracy cannot resist gravity. The question returned, more pressing than before. What happens to stars more massive than the neutron star limit? The Oppenheimer Snyder calculation. In 1939, Hartland Snyder and I addressed this question directly. We considered a spherical cloud of dust, matter with no pressure, collapsing under its own gravity. This is an idealization, but it captures the essential physics. General relativity provides the equations. The Schwarzschild solution describes the space-time geometry around a spherical mass. We extended this to describe a collapsing mass. The calculation revealed the following sequence of events. The collapsing matter accelerates inward. The gravitational field at the surface intensifies. Time dilation becomes significant. Time passes more slowly at the surface relative to a distant observer. As the surface approaches a critical radius, the Schwarzschild radius, time dilation approaches infinity. A clock at the surface, viewed from far away, appears to slow down and asymptotically stop. The Schwarzschild radius is given by r_s equals 2gm/c squared, where g is Newton's gravitational constant, m is the mass, and c is the speed of light. For the sun, this radius is approximately 3 kilometers. For the Earth, approximately 9 millimeters. When the collapsing matter crosses the Schwarzschild radius, something remarkable happens. The surface, and everything inside it, becomes invisible to outside observers. Light emitted from inside cannot escape. The region inside the Schwarzschild radius is causally disconnected from the rest of the universe. We call this the Schwarzschild singularity, though the term is slightly misleading. The singularity is at the center, at r equals 0. The Schwarzschild radius defines the event horizon, the boundary beyond which events cannot influence the outside universe, the view from inside. Our paper also described what happens from the perspective of someone falling with the collapsing matter. From this viewpoint, the collapse does not slow down or stop. The matter falls through the Schwarzschild radius in finite time. There is no barrier, no surface, no special event at the horizon. The infalling observer notices nothing unusual at r equals r_s. But the collapse continues. The matter compresses to higher and higher density. Eventually, our equations predict, it reaches infinite density at the center. This is the singularity, a point where density, curvature, and gravitational tidal forces become infinite. The equations of general relativity cannot describe what happens at the singularity. The theory predicts its own breakdown. From outside, none of this is visible. The outside observer sees the star dim and redshift, its light stretching to longer and longer wavelengths. The collapse appears to freeze at the Schwarzschild radius, but it does not actually freeze. The star continues falling, invisible, toward the singularity. The paper was mathematically rigorous. We solved Einstein's equations correctly. The physics was sound. And yet, almost no one believed us. Why physicists rejected black holes? The resistance to our result had several sources. First, the singularity. General relativity predicts that space-time curvature becomes infinite at the center of a collapsed star. Many physicists, Einstein among them, considered infinite quantities as signs that a theory had failed, not predictions to be taken literally. Einstein himself never accepted that black holes could form in nature. In a 1939 paper published the same year as ours, he attempted to show that gravitational collapse to the Schwarzschild radius was physically impossible. His argument was flawed, but his prestige was enormous. Second, the event horizon was conceptually disturbing. A region of space from which no information can escape violated intuitions about causality and physics. How can a physical object simply vanish from the observable universe? Third, there were no observations. No black hole had been detected. Without empirical evidence, the theoretical prediction remained speculative. Many physicists adopt a conservative stance. Extraordinary claims require extraordinary evidence. Fourth, and perhaps most importantly, there was a war. By 1941, I was consumed by the uranium problem. The fundamental physics of gravitational collapse seemed distant and irrelevant compared to the immediate question of nuclear weapons. I never returned to black holes. The subject lay dormant for decades. The lost years. Between 1939 and 1963, almost no research was published on gravitational collapse. The field simply stopped. Chandrasekhar worked on other problems. I built the atomic bomb, and then was stripped of my security clearance. The physicists who might have pursued this research were occupied with nuclear physics, radar, and the practical demands of wartime and post-war science. The few papers published during this period were largely ignored. David Finkelstein in 1958 clarified the nature of the event horizon, showing it was not a true singularity, but merely a coordinate effect. his paper received little attention. John Wheeler, who would later coin the term black hole, was initially skeptical. He argued for years that some unknown physical mechanism would prevent complete collapse. He searched for a way out. Only in the 1960s did he come to accept that black holes were real. The rediscovery. The revival began in 1963 when Roy Kerr discovered the solution to Einstein's equations for a rotating black hole. Real stars rotate. The Schwarzschild solution assumes perfect spherical symmetry, which requires zero rotation. Kerr's solution was far more physically realistic. Kerr black holes have remarkable properties. The singularity is a ring, not a point. There are two event horizons instead of one. A region called the ergosphere exists, where space-time itself is dragged around the rotating black hole. Kerr's solution demonstrated that black holes could form from realistic stellar collapse. The objections based on perfect symmetry fell away. The discovery of quasars provided observational motivation. These extraordinarily luminous objects at cosmological distances seem to require enormous energy sources. Gravitational energy released by matter falling into a supermassive black hole offered a natural explanation. Pulsars, discovered in 1967, confirmed the existence of neutron stars. If neutron stars existed, then the question of what happens above the neutron star mass limit became urgent. By 1970, black holes were mainstream physics. The theoretical framework Snyder and I had established in 1939 was finally accepted. What we got right. Our 1939 paper made several predictions that have been confirmed. First, gravitational collapse to a black hole is the inevitable fate of sufficiently massive stars. Stars above approximately 3 solar masses, after exhausting nuclear fuel, collapse to black holes. This is observed. We detect black holes in X-ray binary systems, in gravitational wave events, and in the cores of galaxies. Second, the event horizon is a real boundary. Anything crossing it is lost to the outside universe. This has been confirmed indirectly by observations of matter spiraling into black hole candidates, and directly by the Event Horizon Telescope images of M87 and Sagittarius A star. Third, the Schwarzschild radius correctly describes the size of the event horizon. For a solar mass black hole, it is approximately 3 kilometers. For the supermassive black hole at the center of our galaxy, approximately 12 million kilometers. Fourth, time dilation near the event horizon is extreme. Gravitational redshift from matter approaching black holes is observed and matches relativistic predictions. What we did not know. Our 1939 calculation assumed spherical symmetry and pressureless matter. Real stellar collapse is messier. We did not account for rotation. Kerr's solution, discovered 24 years later, showed that rotating black holes have qualitatively different structure. We did not address the singularity problem. General relativity predicts infinite density at the center, but infinite quantities suggest the theory is incomplete. A quantum theory of gravity might resolve the singularity. We do not yet have such a theory. We did not anticipate Hawking radiation. In 1974, Stephen Hawking showed that black holes emit thermal radiation due to quantum effects near the horizon. Black holes slowly evaporate. A solar mass black hole would take 10 to the 67 years to evaporate, vastly longer than the age of the universe. But the process is real. We did not predict gravitational waves. Einstein's general relativity predicts them, but we did not consider merging black holes. The first direct detection of gravitational waves in 2015 came from two black holes merging. Why I abandoned the subject. People ask why I never returned to black holes after 1939. The simple answer: the war. By 1941, I was deeply involved in the uranium problem. By 1942, I was appointed to lead the Los Alamos laboratory. There was no time for abstract theoretical physics. But there is a deeper answer. I was disturbed by the result. Singularities trouble physicists. Infinite quantities mean the theory fails. General relativity predicting infinite density meant general relativity was incomplete, that something essential was missing from our understanding of gravity. I did not know how to resolve this. No one did. A quantum theory of gravity was needed, but quantum mechanics and general relativity resisted unification. They still resist. I wrote about black holes once. I calculated their properties. I showed they must form from massive stellar collapse. And then I moved on to problems where I felt I could make progress. The atomic bomb was in a certain sense tractable. We knew the physics. We could calculate the yields. We could design the devices and test them. The engineering was difficult, but achievable. Black holes offered no such tractability. The physics led to infinity, and infinity is not an answer. It is an indication that we do not understand. The physics of the event horizon. Let me describe more precisely what happens at the Schwarzschild radius. The Schwarzschild metric describes space-time outside a spherical mass. ds squared equals -1 minus rs over r c squared dt squared plus 1 minus rs over r to the -1 dr squared plus r squared d omega squared. At r equals rs, the coefficient of dt squared goes to 0, and the coefficient of dr squared goes to infinity. Early researchers thought this indicated a physical singularity, a boundary where space-time ended. Finkelstein showed in 1958 that this is a coordinate singularity, not a physical one. It is like the apparent singularity of the North Pole in latitude-longitude coordinates. The pole exists. The singularity is an artifact of the coordinate system. In proper coordinates, Eddington-Finkelstein coordinates, or Kruskal-Sekerish coordinates, the event horizon is perfectly regular. An infalling observer passes through it without noticing anything special. But for an outside observer, the event horizon has physical significance. It is the boundary beyond which events cannot influence the exterior. Light emitted from inside asymptotically redshifts to 0 frequency. Information is lost. The information paradox. This loss of information creates a deep problem. Quantum mechanics is unitary. Information is conserved. The evolution of a quantum system is reversible in principle. If you know the final state, you can calculate the initial state. Black holes appear to violate this. Matter falls in, carrying information. The black hole eventually evaporates through Hawking radiation. But Hawking's calculation showed the radiation is thermal, random, carrying no information about what fell in. Where does the information go? This is the black hole information paradox. It has occupied theoretical physicists for 50 years. Proposed solutions involve subtle correlations in the Hawking radiation, modifications to the event horizon, or new physics at the Planck scale. No consensus has been reached. The paradox remains. I did not anticipate this problem in 1939. Hawking radiation was 35 years in the future. But the paradox originates in the basic structure of black holes, the same structure Snyder and I described, what black holes taught us. Gravitational collapse to black holes demonstrated that general relativity makes extreme predictions that cannot be dismissed on philosophical grounds. Eddington was wrong. There is no law of nature preventing stars from collapsing. The physics permits it. Nature does it. The universe is not obligated to be comfortable for human intuition. Infinite densities, event horizons, singularities, these trouble us. But they appear in the mathematics, and they appear to be realized in nature. Black holes also taught us that quantum mechanics and general relativity must eventually be unified. The singularity at the center of a black hole is where both theories fail. Understanding what happens there requires a quantum theory of gravity. We still do not have that theory. String theory, loop quantum gravity, and other approaches offer candidates. None is complete. None is experimentally confirmed. The problem I encountered in 1939, equations that lead to infinity, remains unsolved. Conclusion. In 1939, I helped prove that black holes must exist. The calculation was straightforward. General relativity plus the physics of stellar collapse equals gravitational singularities hidden behind event horizons. The physics community rejected this for decades. Einstein never accepted it. Eddington ridiculed it. The result lay dormant through a world war and beyond. By the time black holes were accepted in the 1960s, I was 60 years old, stripped of my security clearance, my reputation permanently altered by the hearing of 1954. I never returned to the subject. The bomb took those years. History took those years. But the physics endures. Snyder and I were right. Massive stars collapse. Event horizons form. Singularities exist. Or something exists where our equations predict singularities, something we do not yet understand. The paper is still cited. The calculation is still valid. The questions it raises about singularities, about information, about quantum gravity are still unanswered. I spent my later career being asked about nuclear weapons, about Hiroshima, about my regrets. No one asked about black holes. But in some ways, the black hole paper was the more profound work. Nuclear weapons operate within known physics. Black holes take us to the edge of what physics can describe. I stood at both edges, the edge of destruction and the edge of knowledge. One made me famous. The other was forgotten for 30 years. Physics does not care about fame. The equations are true regardless of who believes them. Gravitational collapse happens. Black holes form. The universe contains objects so dense that light cannot escape them. I helped prove this. And then the world moved on, and I moved with it.